Hello everybody, welcome to part 3 of the Sunvox and Pixilang tutorial series, where we continue our quest to create cool music demos for our Sunvox files. In the previous video, I explained how to download and execute the sample code that I explain in the YouTube videos. We showed how to play back a Sunvox file and show a terribly interesting blank window for it. This time we're going to improve upon that demo by actually showing something in that little window. Specifically, we're going to show the modules and show their connections, much like how Sunvox does it, but we're not going to have any text or any cool animations just yet. But at least it'll be a good start into learning how to use Pixilang for graphics. So let's check out what we're going to do this time. I've uploaded a new sample and it's available in the O2 module graphics directory. The previous code sample was in the O1 folder, so I've added a new one for this video. If you run Pixilang in it, you'll be greeted by the familiar file picker dialog that we added before, but this time instead of showing nothing, it'll show something. And this time we can actually quit early rather than waiting for the whole thing to finish. So first we'll go over a diagram of how I have added this and the changes from the first tutorial code. Then I'm going to go ahead and explain some core Pixilang concepts that you'll need if you want to work with the code. And finally we'll do a brief overview of what's new in the code with our newfound knowledge. And that should wrap it up. Okay, let's take a look at the overview diagram for this code sample. All these diagrams are also now included under the docs directory of the Pixilang tutorial project. So when you download all the code, you also get this directory that contains PDFs of all these diagrams, so you don't have to squint at the YouTube video anymore to figure out what's going on. Alright, so what's new is represented by this light blue color. So anything there is new. The yellow and salmon parts were introduced in the first tutorial, and they were the setup and the playback steps to play back our song. But now we've got a new step here that initializes the visualization. And this first function call here for the initialization just collects information about the modules, such as color and position. It's all the stuff that needs to be done only once before we enter a continuous loop of drawing and asking whether we should quit. If the user hasn't quit or the song isn't over, then we draw the next frame and we just keep going. But if the song is over or the user has quit, then we start tearing down everything and then exiting politely. And that's when we call the visual deinit method, which does the reverse of the init method, much like how we previously had a setup and a teardown phase. So nothing really notable there. The main meat of the code sample now is really this visual draw method. In that method, we use the data we collected in the init step to calculate the position of the modules and figuring out how many links are coming out of each of those modules. Then we actually draw the links represented by lines, and then finally we draw the modules to complete the picture. So now let's go over a couple of Pixilang concepts that you'll need if you want to understand the code. So let's go check out those now. The first concept we should talk about are containers. And they're just like what the name sounds like. They're storage for a variable amount of items. For instance, in the visual init method, we want to record what the positions are of all the modules, their XY coordinates. So we could have variables for each one of these modules, x1, x2, x3, and so forth, but we don't know how many modules there are. So if we had 10 variables and there were 20 modules, then our visualization wouldn't work. So that's when we can use containers and initialize the container with a certain size to fit all of the information we want to store. So I've copied some examples from the Pixilang manual that you can also check out. It explains all this in detail, but I decided to show it here anyway with kind of a diagram. So in this first example, A is a new 1x1 container. It's just like having a variable. And the question mark here is it's filled with garbage initially. So we have no idea what value is in it. B is created with 4. So there's actually 4 of these boxes with more garbage in them. C is 4x4. So there's actually 16 boxes, if you can imagine it as a grid of them, since there are 4 width and 4 height amount of cells. And D is the same thing, but a type is specified as integer 32. You won't have to really know the types much. They're mostly going to be integers, but it is good to be aware that they could be of different types. So I've colored D here with a different color. So we already reviewed step 1 here. Use new to create containers. They could be filled with garbage. We have no idea what's in them. Step 2. We can assign values into them. For example, when we collect the module's coordinates, we're going to assign values into the boxes so we can refer to them later. And you can use these brackets to indicate which cell. So if we put A0 equals 1, then the only element of A is assigned to 1. And we can do that with B and refer to specific indices of the container to set their values. And step 3 isn't profit, but we can use the values by indexing them like we did in number 2, except instead of assigning, we just use them directly. And here's an example where we might draw a line of red by indexing into the X and Y containers. And you'll see this a lot because we're going to record a lot of information about the modules into containers and then index them using some variable. And finally, remember to remove any containers you create with new if you don't need to use them. You have a finite number of containers, and if you keep using them, the program is eventually going to quit with an error message. So when you can, make sure to call remove on the containers. Remove A would delete the container for A and free the resources, and remove B would likewise free up B. Okay, and that's it for containers. If you have any questions, again, leave some comments. Let's move on to the next concept that we'll need. The second concept that you'll see repeated throughout this code, and it'll be pretty much what you need to create visualizations, are loops. And a type of loop that we're going to use is called a while loop, which executes some series of commands some number of times. We could just repeat every command we want. Say to draw a module, we could just repeatedly paste draw module, draw module, draw module over and over. But if we use a while loop, then we can save ourselves some typing. So the format you'll see is generally there will be some sort of condition to tell the program that we need to keep looping, and within the brackets it'll have 0 or more commands. So I've provided a little example here that you'll see very often. We'll initialize some counter to 0, and then while that counter is less than some number, specifically we'll be pretty much repeating over all the modules until we've hit the number of modules and quit. And then at the last line of the loop, we usually increment that counter by 1. If you're familiar with programming, it might seem a little weird that we just do I plus 1, but it's actually the same as doing I equals I plus 1. This is a little strange at first, and you can still do I equals I plus 1. So the output for this is just 0, 1, and 2 because we looped while I was less than 3 and incremented it each loop. So this would have printed out I 3 times. Okay, now let's move on to the final concept before we dive into the code. The final concept I'd like to talk about are global and local variables. You might actually not really need them to understand the code, but there are situations where I'll put $signs in front of variable names, and you might be wondering why. So this is why. Global variables can be modified and read anywhere. They don't have $signs in front of them, and they're used to store things that are convenient to reference throughout the code, like the module colors. And the other type of variable are local variables, and they do have $signs in front of them. And these are to be used within blocks of code where you don't want to modify things that are global. They can only be modified and read within the block they are defined in. So take a look at this code sample, and you can review that on your own time to see how they behave differently. But I mostly use local variables so that I don't mess up something that's global and wonder why my program broke and burst out into flames. So I mostly use it as a safety mechanism, but I guess you could go all globals and be pretty much okay as long as you don't use the same names anywhere. Alright, so now that we're done with all these concepts, let's actually dive into the code and see what's different. Alright, let's take a look at the new code in this code sample. The first file, as usual, is the boot.pixie file. It's the first file that Pixilang loads up and gets things going. And most of the code here you've already seen before because it was covered in the first tutorial code sample. The only thing that's really new is we include more Pixie files. And I created these Pixie files mostly for organizational reasons and to define utility functions that are useful for us later. You could just include these functions right directly into this file, but I just thought it would be neater code-wise to put them in separate files. Most importantly, we include our visualization code and put it in a separate file so that we can keep boot.pixie nice and clean. I've added a little more to the while loop, and here, as we discussed, we initialized the visualization by calling visual init, which is now available to us because we did call include. The while loop calls visual draw to draw the stuff on the screen, one frame. Then we check whether the user pressed the escape key. Finally, as in the first tutorial, we check whether the song ended. And then there's additional logic to determine how much to sleep or how much to delay until the next frame, our next call to visual draw, will be. I've documented this in quite some detail, so you can read the comments, and if you have any questions, let me know in the YouTube comments. And finally, the frame call actually transfers all the commands we did and puts something up on the display. And after that looping action is done, we call dinit, and then we leave like we did in the previous tutorial. So let's check out some of the new files we just included really quick. Math.pixie just has two functions so far, called min and max, to return the minimum of the two arguments or returning the maximum of the two arguments. It seems strange that there aren't any functions for these. Maybe I just didn't read the documents clearly, and they're actually already there. But anyway, I put those in math.pixie. util.pixie has one function that I guess I didn't really need to add, but it's called mustLoad, and it just calls load, which is used to load images. And what I do here is if the image couldn't be loaded, then I print an error message and quit immediately. That way if something goes wrong, I'll know immediately and I won't be scratching my head as to why something didn't appear properly. So it's just to help us get things going a little quicker and find out errors with an early notice. Alright, let's move to the big one. Visual.pixie is where all the action will be in the future. And it has the three methods: init, dinit, and draw. The visual init method loads the information about all the modules, and it first starts by loading the PNG image for the module. Add your own PNGs and change this if you want to change from a dot to something more interesting, maybe to some cat or some other animal. We define the width and the height so that we don't draw over the boundaries of the screen. And then we encounter containers for the first time, and we set up various containers to track all the information about the modules. All the containers track one specific aspect of the modules, and so the length of those containers are how many modules there are. So we check whether they exist, the link count, and the color, and the X and Y coordinates. Sunvox has this concept of whether a module exists or not. Modules that I guess were deleted, but maybe they weren't completely deleted. So if you insert a new module, it might come back. But we don't care about those. So only if the module exists, then we collect the color, the coordinates, and we also do some additional bookkeeping to determine the minimum and maximum of the X and Y coordinates. We don't really know what the X and Y coordinates are defined to be in Sunvox. They're just some random numbers within some range. So we keep track of the minimum and the maximum for now. And we also keep track of the range between those values once we've collected all of them, so that we can position them in some kind of position on the screen. Now we get to the draw method. It's actually quite simple. So far we just clear the screen once, and then we draw the modules. The draw modules function is something you probably won't have to touch too much, and it takes the coordinates where you want to draw the module diagram and a size. Right now we just fill the screen with the entire diagram. But if you wanted lyrics on the right and maybe the modules on the right hand side, you might change the width, the height, and the position to draw modules to display it on the right hand side. And this is where the three different steps we talked about in the diagram come in. The first while loop goes through all the modules and calculates the position that they should be in given the center coordinate and the width and height. It's using the minimum and the maximum and the range and putting those all together to position them in this new section of the screen. The next part draws the links by using the positions in the previous while loop. And if the module exists and there's links, it calls the svGetModuleOutputs function to get the links, which are just numbers, and then we draw the coordinates, the links, the lines between each of those modules with white. So if you want to change the link color or don't want links at all, you can remove this loop or change the color here. Finally, we draw the image of the modules on top of the lines, and the image is a circle, and so it covers up the lines when we draw them. So it shows like a nicely neat connected graph. And of course, whatever image you decide to use, you can change it here by loading a different image in the init method. And you don't have to you can call Pixie with any argument. So if you want a background image, just call load with a different PNG and set the X and Y coordinates to maybe the upper left corner and give it a color, or you don't have to give it a color so that it'll display it in the way it looks like in an image editor. Our image is just white, but here we can actually give it the color of the module, and Pixilang will go ahead and tint that image. So that's why different colors are shown. Finally, there's the visual dinit method, and that just removes all the containers that we created in the init method. To be honest, it's really not necessary, because when the program quits, it doesn't really matter whether we remove these or not. But I added this anyway. I guess I don't really need to, and I probably should just delete it to make things simpler in the future. But it's good to have a matching teardown step, I think, in case we really do need to do something in the future. Alright, and that's the code for the second code sample here. If you have any questions or comments, let me know in the YouTube comments, and I'll try to answer as soon as I can. In the next video, we'll actually try to animate things by adding things in the visual draw method that depend on time as it progresses, and also on different values returned by Sunvox for each of the modules, and we'll try to get our demos to be animated. So until then, take care, see you later.